The Coastal and Port Engineering course will be lectured by Dr. Eric C. Cruz. Dr. Cruz obtained his bachelor's degree in civil engineering from the UP College of Engineering in Diliman, and both his master's and doctorate degrees in coastal engineering from the University of Tokyo in Japan. He has done postdoctoral research in Japan and the USA and has more than 26 years of experience in engineering research, hydrodynamics, and wave-related numerical modeling and studies, and engineering and design works for coastal resort areas, marinas, ports, coastal protection engineering, beach development, harbors, land reclamations, coastal power plants, offshore anchorages, and marine infrastructures in the Philippines, Japan, and the United States. He has published more than 157 scientific papers in national and international conference proceedings and journals. Dr. Cruz is a full-time professor at the University of the Philippines Institute of Civil Engineering, a research affiliate at the UP National Hydraulic Research Center, an accredited specialist in water engineering and specialist in energy and environmental engineering by the Philippine Institute of Civil Engineers, and the founding principal engineer of AMH Philippines Incorporated. Ladies and gentlemen, let's all welcome Dr. Eric C. Cruz.
Good afternoon. Magandang hapon po sa lahat. I'm pleased to be in front of you to lecture on my particular specialization, which is coastal and port engineering. Ms. Angelo, can I share my screen?
Yes, sir. You can start sharing your screen.
Okay. Can you see? Okay, this is the presentation on the coastal and port aspects of the gas policy development project of between the DOE and the USDS. And I'll focus on the coastal and port aspects. I hope I'll be able to cover both of these topics in the time that is allotted. As a matter of introduction, let me just show some pictures here that were also used by Professor Ignacio in his lecture, I think 2 weeks ago. This is a picture of an actual LNG facility that shows the coastal and port structures also, in addition to the other aspects of the LNG, downstream gas industry. And well, I'll focus on the facilities that are sited along the coastline, and also the structures that are used by the LNG ship for berthing, mooring, entering the harbor, and that's similar. And just to have some concrete images of the structures. Again, this is from the previous presentations. This shows the LNG facility, including the onshore base depots, the facilities to handle the different cargo from the ship, and also here you have the dolphins and the piers to handle the cargo from the ship itself. And you can see here now looking from the side of the sea, the structures on shore that are typically accessed by the ship, and also vice versa. That means loading by the onshore facilities onto the planes and to the ship itself. As a result of the various consultation meetings and presentations with the different government agencies involved in the LNG business, the GPDP group established came up with this various stages of the LNG industry. And you see here some of the business activities that have been identified and closely studied in this project. You have here the facilities onshore, and then you have the ship, and then you have the facilities that are used to handle the cargo and to move the ship, and also the onshore facilities. You have the depots and the gas handling facilities, and not visible here is the subsea pipelines, which are used to handle also the cargo from the ship. And we're closely moving to the aspects that pertain to coastal, and well, the marine aspects have been discussed by Professor Rogers, I think 2 weeks ago, and well, this pertains to the well, business types that involve this coastal and marine aspects, and these are the ports, and the floating storage units, and then the FSRU, and then of course you have the LNG ships, and the carriers, and also operations that pertain to the either ship-to-ship operations, or operations between the ship and the onshore terminals, pertaining to the movement of both fuel and cargo, bunkering. And well, this is the scope of the coastal discipline, including also the marine discipline. Well, we have the OIT, the onshore import terminal, and under this you have the port and the jetty. Of course, you have the LNG storage and the others that are not really related to ports. On the ports and jetty, you have the siting of the port, design and construction. This involves a different stage of the business permitting and other permitting activities. And in the design construction, we have site development, coastal development, the planning of the port structures, and other components like the fixed structures that are used in the activities for the handling of the cargo. For vessels and floating units, you have these different aspects that are under coastal and marine discipline. And I will focus on the coastal and port engineering aspects that are identified in this scope. Here's the outline of my presentation. Well, it's a long outline, but I hope I'll be able to discuss all of this. So I'll begin with the coastal engineering aspect. We discuss well, these are sections from 1 to 6, and then proceed to port engineering. And under coastal engineering, we deal firstly with the so-called environment loads, and these are enumerated here. The tides, the winds, the waves, currents, and sediments. Tides are due to the planetary forces between the sun, the moon, and the earth. And these forces are affected by the rotation of the earth about its own declined axis, and also by the distribution of the land masses on the surface of the earth. These are important forcing due to the environmental loads, because tides also become the takeoff levels of storm surges and other ocean hazards. Winds, they will exert shear stresses on the sea surface, and these stresses in turn affect the sea hydrodynamics that pertain to the water surface levels, the currents, and the waves. Also, winds become forcing functions to the drag and inertial forces that are exerted on docking facilities, as well as the moored ship. The third one is waves. These are the perpetual loading on all marine and coastal facilities and vessels, It's very important that you understand the nature of waves and how they transform in the relatively shallow waters of the ports. This is the main forcing also on coastal structures. Most coastal structures need the information, the wave conditions in order, well, for design purposes. And waves, of course, can penetrate harbors, marinas, and similarly enclosed structures. The third environmental load is the current, and currents exert that drag on reverse bodies that includes the ship, the piles that support the piers and other marine facilities, and also the anchors and breakwater armor units, the quay walls and the scar protection work. They cause also marine scar on infrastructure. So it's very important to quantify currents when designing protection structures for ports. And finally, sediments, they affect the long-term stability of the coastlines. That means the shape of the coastline not taken from above, which we call morphology. And also the bathymetry of the leisure area. That means the shape and the slope, etc. They also cause short-term changes. That means seasonal and storm, and this affect the closure profile that in turn affect the waves. And sediment characteristics are related to marine scar of infrastructure. So we need to know the size and the density of the sediments that are around our structures in order to estimate, calculate the marine scar that will be generated by the action of the currents and the waves in these infrastructures. On the other hand, if you have siltation, this means that there will be some changes, particularly decrease in the ambient depths of ports, and that means that there will be some necessity of maintenance dredging of these ports and harbors. This siltation also causes amplification of the wave energy in river outfalls. So it's important to locate where outfalls of rivers from inland carrying surface runoff will be in relation to the port location. Just to have some idea of how waves, which are the perpetual loading on all marine structures, including the ship, transform in the nearshore zone. Normally, we know the conditions of the waves in the deep water. That means they are not affected by the processes and phenomena that occur close to the shoreline, and even by the interaction of waves in the with the vessels, with the ship, and with other moving elements in the ports. So what we normally do is to predict the transformation of these waves in the nearshore zone. For example, waves will undergo so-called wave diffraction, in which case the direction of the waves will tend to change as they reach shallow water. They tend to move as if they want to approach a normal direction, that means perpendicular to the shoreline. And the other process is the wave reflection. If you have some obstructive structure like a rubble mound breakwater, they will get reflected because of the presence of these boundaries. You also have wave damping. If you have a porous structure, then in addition to the reflection, some portion of the incident wave energy will be damped, and only a fraction will propagate towards the shoreline. Very important to port engineers is this process of wave diffraction. If you have an obstructing structure here, or element, like an island, or a breakwater, then waves tend to permeate, or leak around the edges of corners, like this. So this is called wave diffraction. This is very important to port engineers because in ports, you have some protection structures like breakwaters and detached structures that are intended to protect against wave attack. And we need to quantify the level of protection that is afforded by the structures by computing the so-called wave diffraction effects. And finally, you will have some beach reflection. As the waves hit the coastline, they will be partially reflected back into the sea. This well, in the coastal area, no, especially those who are familiar, no, with the those who frequent the beaches, no, during summer season, they are very much aware, no, of this shallow water wave transformation, the so-called shoaling effect, no, where the waves grow in height, no, as they reach the shallower water. No. At some point, no, they will break, no, so they will attain their maximum height at some distance from the shoreline. No. And if the sea is monotonically decreasing in depth, no, they will continue to break, no, until they swash up, no, the swash zone, no, in the backshore. And finally, you know, if you have coastal structures that are very close to the coastline, no, and waves hit them, no, then the hydrodynamics will change, no, from a pure oscillatory field, no, well, the seawall of these structures, no, once they interact with the structures, they will cause, no, some nearshore currents to be generated, no, including the so-called longshore current, no, and we have this circulation cells, no, and these are very important processes that port engineers, no, and also coastal engineers need to be enumerate about, no, be able to quantify. And finally, you know, recently, you know, some types of breakwaters that are not visible from land, no, called submerged breakwaters, no, these have been these have become popular, no, in the last 2 decades, no, in many countries in Europe, no, and North America, no, and even in Asia, no, in China, no, and in Japan, no. The submerged breakwaters, they are not visible from land, no, because they are submerged, no, but they induce, no, a different set of processes, no. Well, in particular, no, the so-called wave decomposition. But this one is this topic has been actively researched on, no, and most of the we have an almost complete knowledge of how this wave decomposition happens. No? Some applications of wave transformation in the planning of ports. No? This is a so-called coastal engineering 101 case. No? The case of the so-called El Segundo Wharf, no? In El Segundo, California. No? You have this coastline of El Segundo, no? And the company, you know, that in the 1970s, no, there was an oil shock, no, because of the sudden closure, no, of the oil fields in the Middle East, no, and one oil company in the U.S., no, suddenly put up, no, a wharf, a big wharf in El Segundo, no, without the benefit of a coastal engineering study, no. And what happened is that, during a certain critical condition of the wave approach, no, from the ocean, no, from Pacific Ocean, in particular, this wave direction, 280 degrees azimuth, no, with a wave period of about 18 seconds, no, when, this is the refraction diagram that shows, no, the distribution, no, of the wave direction, no, in the area. No. So these lines, no, show the direction of the waves. No. And you can see that if the waves are coming from the Pacific Ocean, no, from this direction, 280 degrees azimuth, no, they tend to focus on this area, no, where they built their mammoth, no, wharf, no, for the unloading of the oil, no, from the ship. No. And after construction, no, they had a hard time, no, docking the ship at the anchors, no, at the wharf, no, because the sea was very agitated. No. And they tried to retrofit it, no, by using structural retrofitting techniques, no, thinking that the problem was due to the light mass, no, of the deck slab, no, that they used for the stockpiling area, no. But after some time, no, after investing a lot, no, on the retrofit and also on the initial construction, no, they finally left, no, the area, no, because this resort was given to them. It shows that the area was unfortunately in the area of the so-called wave concentration, no? And there is a wave amplification there, no? And of course, after spending a lot on the structure, no, they finally abandoned the site. No? Well, if they just studied the area, no, they would have learned, no, that there is a very good area to the north of their property, no? And that is in Santa Monica. No? And this is an area of wave modulation because the wave rays are actually diverging, no? And that means that the waves will be very low, no, there, and therefore it's a good site, no, for their oil work. No? This is another case, in the other side on Hudson Canyon, no, on the east side, no? the US. No? There was a coastal harbor that was being contemplated in this area. No? It's a recessed area, no? Where a coastal harbor was already, being used, no? Temporarily. No? But the state wanted to place, no, a permanent structure there, no, by placing a detached breakwater, a pair of detached breakwater there. No? There is a small area that connects to the inland navigation system. No? So this is a very important area, no, for the both for the sea navigation and for the inland navigation. No? But when they did analysis, no, for a particular wave approach, no, this is a wave period of 12 seconds, no, with an azimuth of 112 degrees. No? So this is the direction of those. No? And they did analysis. No? There is a canyon here, which is like a deep ravine, no? Which is elongated, and that's causing all the waves to focus on the area there. And you have areas of wave amplification, no? Where the wave rays intersect. No? That's an area of wave agitation. And of course, the good area is where the wave rays, no, diverge. No? So that is, for example, this one area of wave modulation. So this is a good site, no, for the planning, no, of a port or harbor. Just as a reference for the planning, those who are involved in planning. If you have, for example, a state coastline, no, with straight and parallel bottom contours, those contours of depths are the dash lines here. No? If waves are coming from the, for example, from the southeast, if you draw the direction of the wave, it's normal, no, to the so-called wave crest lines here. No? So the waves tend to, they tend to bend, no, towards the shoreline, no, like this. No? So here it's like this, no, but at the close to the shoreline, it's already almost normal. No? And at some location, no, at some shallow water, no, the waves will break, no? And the breaking locations, no, are indicated by this XXX. If we have a straight coastline, no, but the depth contours are like this, no, what we call a submarine ridge, no. So it's not straight like this, no? But if you have a submarine ridge like this, which is like a ridge, except that it's below the water, no? Then if the waves are coming from the south, no, they tend to concentrate, no, in this area. The wave rays converge, no, in this area. But that means this area is a region of very agitated waters. No? The waves are high, no, in that area, and the waves are coming from various directions. No? So it's a very agitated area. No? It's not good to put a port in that area. No? If you are limited to this area of port planning, no? Port location, no? Then the area that is best, no? Under this condition is, this area that are where the wave rays are diverging. So that means that the waves will have a well-defined direction. At the same time, the wave heights will be small. No? This is another type of very common bathymetry, a straight coastline, but with now a canyon in front, no? A submarine canyon. So it's like a, in the case of hydrology, no? These are like valleys, no? That are, except that they are submarine. No? So if the waves are coming from the south, no? The waves tend to focus, no? In the area, no? To the side, not to either side of the canyon, and they tend to diverge, no? In the in front of the canyon itself. No? So that means it's a good the area that's in front of the canyon is a good site, no? For a port. In reality, Philippine coastlines are mostly of this type, no? The bay coast, no, and headland coast, no, type. No? You have a bay here, no? An embayment, no? And then a headland coast, no? And then embayment, no? So alternating embayments and headlands. No? If the depth contours are shown by the this dash lines, no? And the waves are coming from the south, no? Then the refraction diagram, no, for this area will be as shown by these arrows. No? That means that in front of the headlands, no, the wave rays, no, concentrated. That means you have agitated conditions there. No? In front of the bay, no, the area, no, of course, is you can see that they are diverging. So that means it's a tranquil zone. No? But for practical purposes, no, when siting for example, a temporary docking area, say, this is very common in many Philippine construction sites, no, where the materials from for a coastal area, no, are usually brought from another island, no, offshore. No? Then the ship will have to dock, no? At the most practical case, no, that for example, a ship with a draft requirement of 4 meters, no, can dock here, no, because the required length of the pier, no, is close, no, is short, no. That means you can easily find, no, the 4-meter depth, no, just a few meters, no, from the headland itself. No? But of course, that is an agitated area, no? So that means even though you have a pier, no, you cannot, the ship cannot dock there, no, because the wave condition is very agitated. No? So as a matter of compromise, no, well, if you place the pier here, no, then it's not it's good for the wave tranquility. No? That means the waves are low. But of course, in order to reach, no, the required draft of the ship, a long pier has to be built. No? So as a matter of compromise, no, normally the siting of a port, no, along a bay headland coastline, no, is a compromise between the headland and the bay. Normally, it's between the two of them, where the pier, no, is recommended to be built. Okay. Wave breaking, no, is very important to coastal engineers because they provide the threshold, no, of the so-called maximum growth of the wave. No? So whenever you have a breaking zone, or you know that the wave height is maximum at that area. No? So these are some of the pictures of different types of wave breakers. No? So you have this spilling type, no? The most common is spilling type. No? And then we have the plunging breaker, which wave surfers like. No? They look at the site where the breakers are plunging, no? And not anything else. No? And we have this other type of breaker called the surging breaker, no? Which is like the hydraulic jump, no? In many spilling basins, no? Stealing basins of dams. No? Well, the Japanese, they have a fourth type called the collapsing breaker. But anyway, we normally determine the type of breaker, no? Because first, no, it is the threshold, no, of the wave growth, no, the wave height growth. No? And if you have a structure that is in the so-called surf zone, no, that is delineated, no, by the location of the breaker, then the wave forces that are extended on the structure, no, same structure, same size, same height, same length, no, same depth. Then if the waves are breaking there, no, then the forces, no, extended on that structure will be greater, no, than if the waves were not breaking. And also 3 and 4, they instead of just pure wave action, no, they will have cross-shore currents, no, generated by the wave breaking process. That means that if you have cross-shore currents, no, you will have active entrainment of the sediments, no, with the flow. No? And that means there is a possibility that you will have erosion of the coastline and accretion in some other zones. These are some of the, because we have limited time, I will not discuss this. These are some of the things that coastal engineers analyze, no, in the coastal area. No? For example, when doing a design of a port, no? Well, we have a coastal port here, no? A coastal harbor, sorry. Where you have a harbor, no? And we have a pair of coastal jetties here. No? The coastal jetties make sure, no, that the entrance to the waterway here is always navigable. And this is made possible by making sure, no, that the so-called littoral material, no, on both sides of the outfall here, no, are stable. They do not bypass the entrance here. No? Otherwise, no, this entrance will be non-navigable, no? And therefore a hazard to navigation. So what we do is to quantify, no, the effect of the diffraction. For example, if there's a breakwater here, to make sure that this area is passable, no, by say sea flying and say river flying vessels, no, then this area is always safe for navigation. You will have also a case of construction of ports, no, when the bulkheads are still being constructed. No? They are usually constructed with shells. No? So you have here some spaces that are still open to wave action. No? Well, it's an actual case, no, in Japan, no, that I got involved in this project, no, called the Hitachinaka Harbor. No, it's a 40-meter deep, no, transshipment hub, no, along the coast of Tohoku, no, which is northeast of Tokyo. No? And this is actually a 3.5-kilometer long, no, Quayside breakwater. And our construction engineer, no, in Toa Construction, no, figured that they want to build that long breakwater this way. No? I don't know why they decided so, no, but this is how they built it, no? And then the main bulkhead, no, here, is constructed from reinforced concrete shells, like this, with gaps, in between. So, well, this is how the waves will diffract around these breakwaters and the gaps between them. Well, also islands, they cause diffraction. So you can see that these islands will cause these diffractions. So in the case of port planning, for example, if you have a coastline like this, and the main breakwater is configured as shown here, then what is done when the computers were still not very powerful? Well, if the waves are coming from the south, for example, like this, what is done is to first do a diffraction computation up to a certain depth, where the waves do not feel the bottom yet. And then after some time, from that point on, diffraction analysis is done. So these are separate processes when computers are still not powerful. But nowadays, we don't do this. We use a nearshore wave model to determine both the all the wave conditions, including the currents generated at the breaking point. I will skip this. These are some of actual port projects where wave penetration analysis was carried out. This one is that mammoth transshipped hub along the coast of Tohoku in Hitachinaka Port, which is a 40-meter deep transshipment hub, which will handle some ports from North America through the Pacific Ocean. And this long breakwater is 3.5 kilometers long, and then we have here the main bulkhead, and then we have the berth there, and then we have a pier here, and then we have some smaller berths there. And we did some analysis for the construction stage that I showed you in the previous slide. And then this one is in Hiratsuka Harbor. This is southwest of Tokyo Bay, so this is Zagami Bay. And this is facing Pacific Ocean. There is a small island called Oshima Island here that's partially protecting the area from the hazards in the Pacific Ocean. And at one point, this was in 1997. At that time, the harbor Hiratsuka Harbor in Kanagawa Ken was used mainly for commercial fishery. That means that the fishermen in the municipality were using it to load and unload their catch. And after some time, they figured that they learned that the income from this harbor was dwindling. And they found that the reason was that the fishermen who became richer, they did not engage anymore in commercial fishing. Instead, they had recreational boats and yachts, bought, they do not do commercial fishing anymore. So there was a decrease in the demand. So, but the municipal administration did this was to partition the original either bay into two bays, one serving the now decreased demand for commercial fishing, and the other one now catering to the recreational demand of that area. So what we did is to analyze the effect of partitioning the inner bay, so that we see how the interior will be affected by the construction of this partition of the harbor. This is another project case in Japan. This is Nagasaki Harbor in Nagasaki Prefecture. So this is the southwestern part of the third largest island in Japan. So this is close to Okinawa. So the project site is here. It's facing the Sea of Japan to the northeast, to the northwest. And Nagasaki Bay is there. The project site is at the mouth of the bay here. So, it's the original docking area is a wharf used by the fishermen here. But they learned that it's exposed to the open sea, and we have waves coming from the Sea of Japan here. So this is a simulation of the waves coming from the open sea, and they decided to place a long caisson breakwater here to deflect the waves that are causing extreme agitation in the wharf area of the fisherman. So you can see here that the waves are reflect. well, this deflect the waves from coming from the west, not towards the north. No? You still have the penetration of the waves, no, inside the white field. So what the fishermen like to know, no? If they place this caisson breakwater, no, detached caisson breakwater, this is a long one, no? So this is about 1, 2, 3, 4, about 2 kilometers long, no? And this one is well, they want to know the period, no? The wave period that will obtain, no, in this area, no, because that's needed by the fishermen to program, no, their loading and unloading operations. I think I have only 5 minutes now. Let me just take up the other environmental laws. This is sediment transport process. No? You have two types of sediment transport process. One is induced by the current. No? The other is induced by the wave. No? So this one project type in the country, no? That an actual project, no? Recently undertaken. No? That well, one part of the project is to analyze, no, the resulting so-called longshore sediment transport rates. No, so these arrows, no, show the directions of the longshore transport induced by the waves. The waves break, no, they will induce some current. No? The current will try to carry the sediments that are small enough. No? So these vectors, no, indicate, no, how the intensity of the currents, no, that are induced by the waves. No? The longer the vector, the higher, no, the longshore current, no, that will transport the sediments. No? So for many reclamation projects, no, this study is necessary, no? Because the modification of the water basins by the placement of the reclamation, no, will modify the sediment transport pattern. No? It is not well, it's not enough, no, that only the island is studied. It's also very important that the effect of the island on the other adjacent coastlines, no, be studied as well. No? So this shows, no, the changes, no, in the sediment transport pattern when you have a reclamation area like this. No? Well, originally there was not, there wasn't any island here. No? So it's going to change. No? For example, this one downstream, no? Before the construction of this island, no? Actually changed, no? Like this. No? So the pattern, well, the directions changed. No? Also, the so-called total transport rate, no? Which is needed for the determination of the volume of backfill, no? That will have to be placed, no? Along the shoreline. It's not directional transport, no? So you can see here, no, the changes in the so-called gross transport rate. No? So this is very important for both the ports, no, and reclamation projects. No? Okay, I have only 3 minutes, no? So I'll discuss coastal hazards. No? Well, hazards are in this country. You know, we are unfortunately, you know, in that part of the world where there are very active tectonic activities, no, seismic activities. No, we also have, as a result of these seismic activities, we have also tsunami-genic, no, processes that are affecting us, no, both from different places, no, called the transoceanic tsunamis, no, and also nearshore tsunamis, no, just within our area of responsibilities. No. So, well, this coastal hazards, no, pertain to storm surges, no, typhoon waves, no, coastal flooding, no, wave overtopping, marine scar, no, seaching, no, and tsunamis. No. So I will discuss the first one, which is very, very common to us, no, very frequently occurring, you know, in this country. You know, this is the storm surge and storm waves. For example, this is a vertical profile of the area, coastal area. If you're you're trying to plan a port for LNG facilities, no, then the analysis of the hazards, no, because LNG facilities, including the LNG ship, are very sensitive, not to the motion of the ship. If a certain threshold of pitching and rolling motion of the ship is exceeded, no, then the LNG ship, no, may experience you know, some deformations, no, displacements. At worst, no, it becomes internally unstable. No? That means the internal stresses of the ship's hull, no, may be exceeded. No? Well, anyway, you have here, no, coastline. No? Normally, you have a mean tide level. No? And then, of course, because of the tide action, no, planetary forces between the sun, the moon, and the earth, no, well, the sea will oscillate, no, and at some point, no, during a high tide, no, the astronomic tide is here, no? And then here comes a tropical storm, no, and then becomes a typhoon, then super typhoon. No? By the time that super typhoon, no, reaches the coastline, they would have induced a so-called cyclonic wind field that will exert shear stress on the sea surface, and then that's going to increase it's going to uplift the sea level, and that's what we call a storm tide level. So this is the storm surge. So that's acting during a high tide. If you notice the total lift of the sea surface from the mean tide level, it's this much. And then you have the waves, storm waves generated by the action of the wind shear stress on the sea surface, that would induce this waveform. So, for example, if the storm tide level is already above the ground here, there will be coastal flooding, regardless of whether you have waves or not. So it's very important that piers, for LNG ships, especially if it is an open deck pier, is placed above the so-called storm tide level. And okay. Yeah, there's a signal for my time, so I need to wrap up. So well, anyway, well, we place, we do our vertical sighting of the pier, for the vessels, taking into account this storm tide level. Again, the best sighting is of course above the storm wave here, but that can be quite prohibitive in terms of economic cost, and some other considerations. Okay, I think it's already time. I think I will have to. Tama ba? And do I still have time? It's already time.
Go ahead, sir.
Sige. Well, if you have a coastal protection structure like a breakwater here, not a pier, then we still need to instead of, well, on top of the storm tide level, we also need to account for the action of the wave as they interact with the structure here. One particular case is a run-up of the wave like this. So normally, if the structure is not high enough, there will be some wave overtopping. And this is, well, that wave overtopping is taken into account in the design of the structure as well as the protection of the coastline. The other hazard is tsunami. So this is it's not an updated map of the tsunami-genic events in the Philippines. So this is the Philippine archipelago. You can see the geographical distribution of some tsunami-genic events. Tsunami-genic means that there was a seismic activity that caused a tsunami in the area. So this is well, you have here the geographical distribution of the tsunami events. The coloring is based on the casualty. The bigger orange means, well, red means very high casualty. So sorry, this magnitude. So red means that it's that the seismic magnitude is more than intensity 9. Sorry, magnitude 9. And sorry, the color is number of deaths, casualty. And the size of the circle is the intense magnitude of the earthquake. And well, we had several studies done on different places in the country. One that I present here is the one done for Davao. Well, here, there's a bay, there's well, Davao Gulf. It's a large water body. In this area, there is a Davao fault line that runs parallel to the coastline of Davao del Sur and Compostela Valley. And well, in 2012, there was a tsunami that was generated by that gulf, by that fault line. And we did the simulation of the propagation of the tsunami. And that, well, sorry, this one is not in Davao. This is from another site. That's not in the. It's a far shore tsunami that was generated in the Pacific Ocean. And we did the simulation of the propagation of the tsunami. So you can see here some snapshots of the simulation. And then what, well, our interest here is to see how this tsunami will propagate in the enclosed areas, and the port areas adjacent to the source. So that includes Davao Gulf. So you have Davao here, and then you have this Samar Island here, and Talikod Island here. Well, you can see the propagation of this. This is in Davao. This one is, I think, well, somewhere in Bicol. I think, yeah, this is in Legazpi Port, which is also an enclosed an oblique, no, elongated water body, which is very susceptible not to tsunami penetration, no, because of their plant form, no, and their shape. No. Well, we did the analysis there, and then we compared with the results. No, so these are some of the results that we got. We in tsunami, it's important to have the maximum magnitude, no, simulated. No? So we did some simulations, and we got good results, no, as far as the maximum oscillation of the water surface was concerned. No? So we are now continuing with this. No? Hopefully, we'll produce some more research results. No? Well, I will end here, no, because of I think it's already time. No? Tama ba,
Yes,
Ma'am
for
Angela?
the part one.
Okay. Sige. Thank you. No?
Right. Thank you, Engineer Cruz. So we will continue our training session on coastal and ports after the break. Please be back here by 3:25 and also get ready for a short quiz game and win our prizes. See you in a bit. All right, so now let's proceed na to the part 2 of coastal and port engineering session. Once again, Engineer Eric C. Cruz.
Thank you, Angelo. Let me discuss now the second part of this presentation, which is on port engineering. So let me share my screen. You see it?
Yes, sir.
And this is the port engineering aspect of the coastal and port discipline of the GPDP project. This is the outline of this particular topic. No? So we start with the port siting and end with the key walls. No? Port siting. So you asked, no, how is a contemplated site, no, for a port assessed? No? In the case of multiple possible sites, no, like what is usually the case in many private port developments, no, then you will have to choose, no, among such multiple, no, possible sites. No. I will say a story, no, about an actual project that was done, no, but of course this is not a government port project. No, it's a private port development, no, involving the planning, no, and siting of a cargo port, no, in Calatagan, no, in Batangas. So this is the coastline of the area that's being contemplated to locate the site, locate the port area, the port site. And this is the data of the bathymetry. No? This line is the coastline. No? You can see that the from the aerial photograph, no, that the area of the backshore, no, is relatively undeveloped. No? There are no habitation here or engineering developments, no, in the backshore. Well, there are 5 sites that are being considered, no, for the location of the cargo port. No? These are shown here, no, from north to south. Part of the contemplated coastline, no, you have sites 1 to 5. No? So, well, the total area is not so big and not so small. Also, 800 hectares. No? And well, these are the 5 sites. No, this one is site number, I think, number 1. So there is this is the shoreline, no? And because of the size of the ship, no, that are expected to use the port, no, we have this sighting for the drop of the ship. No? After knowing the drop of the ship, we do some adjustments there, no, for different elements of the sighting process. No? That means we take into account the draft of the ship, no, and then the low tide, no, and then the so-called squat, no, of the ship. No? and then other parameters. No? Even the effect of the so-called turning basin. No? If the turning basin will be used, no, then you need to have allowance, no, for the draft of the ship. Finally, after that depth is computed, no, based on the required draft of the ship, no, then these lines, no, this solid red line and the solid dash line, and then the dash line here, no, are the locations, no, in which the minimum, no, required depth of the ship, no, of this two ship, no, the marine vessel Icarus and Panamax, no, can be placed. No? So you have those reference lines here. And again, no, you will have a set, well, as the ship navigates, not towards the pier, no? Then it has to turn around a certain area called the turning basin. No? So, well, the size of the turning basin is usually dependent on the so-called overall length, no, of the ship. No? So ships, they have this geometrical parameters, and from these parameters, we can estimate, no, we can determine, no, the area of the turning basin based on some guidelines. No? In this case, the standard port handbook, no, guidelines says that you need to have a certain turning basin like this. So with that, we can plot the layout of the turning basin, no? And then, well, depending on what is the conditions of the shoreline, no? Maybe that area is not accessible, no? Because it's not part of the property. No? Or maybe because that area is not suitable for, say, the onshore structures. So maybe the soil is soft. No, you cannot found a say a wharf there, no, or a marine terminal. No? So some areas cannot be used to connect, no, the well, this pier, contemplated pier, to host this ship. No, well, along the possible, no, coastline. No? So, well, in this case, no, an oblique alignment, no, of the main trestle, no, to connect to the pier, no, is chosen. No? So that involves a length of 530, no? And the length of the pier equal to, length of the pier, which is proportional to the length of the ship, no? Which is 300 meters. And then you draw the turning basin, no? Here. All right, you do this for the other sites, no? So the other sites are done, are drawn in a similar manner. No? You have here, no, a site that is just close to the tip of this peninsula, no? This in Calatagan. No? So there is a peninsula that's well, if you go around it and go to the southern portion, no, that's already relatively exposed, no, to the hazards, no, of the seas and the oceans. Anyway, that is done for the rest of the 5 sites. No? So after all this preliminary, plotting and superimposing, of the required water basins, is done, no? Then a relative comparison, no, of the characteristics of the site. No? Well, in terms of different criteria. For example, the length of the trestle that is needed to connect to the land, the marine terminals, no, to the pier. No? Also, the maximum vertical distance to the seabed, no, because that's going to determine the length of the piles, no, that are needed to support the pier. No? Also, the soffit elevation, no, which is if we assume that the pier will not be overtopped by the waves during a storm, no, then this is obtained from an analysis of the well, your storm surge, no, and the storm tide, no, that I discussed in the first part. No? And then also the design wave height. No? The design wave height is very important in the sizing, no, of the piles, no, and the slab, no, and the wharf, no, and the trestle, and everything else, no, will depend on the wave height. So this is very important. No? And then dredging requirement. We have a turning basin. No? That basin has to be navigable, no, by the expected ship. No? And therefore, we compute also if there is any dredging that is needed for the turning basin. And then the landing alignment. No? Well, these ports will use trucks. No? So if you have a bad alignment of the trestle, no, the trucks cannot easily enter. No? So you must have a good access, no? Transport access, no, to the trestle in order to have a good pier design. No? Well, with these coastal engineering considerations, no, we rank the sites, no, and these are the numbers that are obtained, no, from each of the analysis, no, of in the preceding slides. No? And then we also do the analysis of the wave heights and the storm surge, storm tide levels, no? That is to determine these two, soffit elevation and the design wave height. No? Finally, we have a matrix, no, of the so-called siting suitability of each of the candidate sites. No? And well, we translate this not to some kind of ranking. No? So you have actually 1, 2, 3, 7 sites actually, no? Because site 1 has 2 possible alignments of the port, no? Of the pier, no? And then also site 2, no? So in total you have 7, no? From this number crunching analysis, no? And preliminary design, no? The enumerate assessment, no, of the possible sites, no, can be done, no? And this is the result of for that particular project site, no? And it seems that well, from this analysis, no, the last site, no, site number 1 yields the lowest, no, score, no? And well, the lower the score, the better the site characteristic, no? Like UP grades, no? So the lowest score is the one that is well considered, no, for well initially. But you also have some other criteria, no, for the siting of the port, like those that do not require well post-engineering well that do not directly bear, no, with the post-engineering considerations, no? For example, the area for port development, also the inland topography. If you have a rolling topography, that's quite hard, no, for cargo ships, no, to negotiate, no? Also, proximity to the existing roads, no? Of course, it's better to have existing roads, no? Because the cost of the civil works, no, and the transportation network, no, will not be prohibitive, no? Well, these are some other considerations that we term here operational conditions. And then you can also do the same numeric analysis, no, for the 5 sites, no? And well, if you combine, well, in this particular set of criteria, no, the third site, no, site number 3 yields the lowest score, no? So now you're down to site 3 and site 5, no? So if you combine all the sites, no, with equal weights, no? Well, normally we allow the owner of the port, no, to determine which one is more important to them in terms of planning, no? Also cost, no, and also land acquisition, no, in other considerations. So with this weights, no, we can do an objective analysis, no, of the suitability of the port site. The one that yields the lowest score here is number 5, no, site number 5. So actually, that's the one that was chosen, no, by the owner, no? So based on this matrix. Well, for the vertical siting and the storm surge analysis, no, well, some graphics like this are normally needed, no, to be able to do the number crunching. So we normally have, well, this shows, no, the color shows the wave height, no? And arrows show the direction of the waves, no? And then these are superimposed on the platform alignment of the turning basin and the pier and the trestle. Well, these are all inputted into the matrix, no? So that an objective evaluation of the suitability of each site, no, can be undertaken. Harbor tranquility, no? Well, after the site is selected, no, normally you have to now go into the so-called engineering phase, no, of the design, no? Normally we do first, no, the so-called preliminary engineering, no? So we lay out the structures, no? And then after laying out the structures, no, then we need to assess, no, the so-called tranquility, no, of the harbor, no? After setting up, no, the different spaces, no, for the say the piers and the docks, no, the berth, no, the main protective structure, which is the breakwater, no? And then if you have other special requirements, for example, for fuel, no, or for dry docking, no? Or say for transit sheds, no? Or say for some other types of cargo handling equipment, no? Or even for customs and quarantine, no, facilities, no? Then this can be all put into the layout of the harbor, no? Finally, after the harbor is laid out, no, a tranquility analysis of the harbor must be done, no? If the harbor tranquility is bad, no, then all the structures, no, inside will have to be designed for large wave height, no, or high currents, no, or very intense, no, sediment transport rates, no, or tides that can easily penetrate through the gaps and entranceways of the harbor, no, which is undesirable, no? So a general tranquility analysis should be done, no? So well, because we have limited time, I will not discuss this, no? There are some principles, no, to make the interior of the harbor, no, tranquil, no, or at least amenable, no, to the docking and anchoring, no, of ships, no, and other vessels, no? And the first principle is that the harbor should have a broad interior, no? So it says here a broad interior. For example, well, nawala yung figure, no? I think I cropped it out. But anyway, it has to have a broad interior, no, not a narrow and congested interior. And then second is well, if you are designing the walls, no, the inside boundaries, no, of the harbor, no, then the well portion of the waterfront from where the outer sea can be viewed through the harbor entrance, no, should be left as a natural beach, no. If it's just a beach coastline, there may be no need to make it a say a bulkhead, no, or a revetment, no. In the first place, that will entail cost. No? Second, it may modify, no, the wave conditions inside. No? So you want to leave the part that is, for example, this is a beach area, no? And then you have a quay here that runs north-south, no? And then okay, this north, no? So this running, yeah, north-south, no? And this one is running east-west. No? So there's a wharf there, no, used by the ship to dock, no, or to moor. No? But there is well, this natural beach between the two of them. No? There's no need to make this a stick boundary. No? If there's no such a need, no, then we should leave this area, no, as a natural beach. No? It's not necessary to develop it into an engineered course. No? Well, we want also wave absorbing revetment, for example. No? Well, okay, that's shown in the next slide. No? For example, here are some layouts of the harbor, no? Where well, the location of the so-called revetments, no, which are wave energy absorbing structural features, no, they tend to make the harbor tranquil, no, and not agitated. No? So we need to place these revetments at those locations. No? These are determined by, you know, you look out, no, from this area, for example, and that imagine that you look out to the sea. No? If you can still see the sea, no, from where you stand, no, that means that you need a revetment there. No? So, for example, no, if you look here, no, and you look towards the northeast, no, you will see the northeast, no, if you are standing at this corner. Therefore, you need a revetment there. So you place the revetment along this line. No? Also here, no, you need the revetment, but in the interior here, no, there's no need for revetment. If you have a harbor layout already, no, then you can determine the locations that need this energy dissipating, no, coastal revetments. Well, this is for well, this is not really for ports. No? These are for marinas, no? But I will not discuss that anymore. No? Well, anyway, well, okay, this is a port. No? Normally, ports have docking structures like wharfs and piers. No? So, well, here you have the main breakwater. No? A pair of them. No? They are both attached to the shoreline. No? And between these breakwaters, you have the main navigation channel, no? The entranceway, no? To the harbor. No? So here, no, waves are coming from this direction. No? And well, if you analyze, no, the penetration of the waves here, no, you will see that you need to put a revetment here, no, in this area, so that the waves will not be reflected. No? Once inside the structure, no, they will hit some walls there, no? And walls tend to reflect, no, the wave energy. No? In order for the wave energy, no, to be not reflected, no, by these reflective walls, no, some areas need to be revetted, no, like well, these locations that are in XXX, no, are revetted areas. No, this need to not to be designed as revetments. No, that means non-reflective, no, but dissipative structures. No. Well, anyway, these are some of the principles that are applied, no, in the preliminary design of the harbor. No, once the layout is done, no? Then the preliminary engineering, no? This starts. No? For example, for this elongated harbor, no? With the main breakwater here, a secondary breakwater there, and then there are two bays, no? The outer bay and the inner bay. Even in the inner bay, you have a small berthing area. Well, this area, this side, no, must be a revetment, no? And not a wall. No? So that means that if there's anything that reflects, no, from, for example, this well, if you have a wave that comes from, say, from the northeast, no, goes like this, no, tends to be reflected at there, no, and reflects like this, no, and then there, and then here it will not be reflected anymore. No? So it stops there. No? So, well, the lake that needs to be revetted, no, is as indicated by this XXX. Okay. Well, these are some other principles, no, in the design of the harbor, no, for tranquility, no, wave tranquility. I will not discuss them in detail. No? Breakwaters, no? As you saw, no, the breakwaters are the main protective structures of the port. No? If you have a harbor, no, without any marine terminals, no, that means it's a harbor and not a port. No? Then you may still have, you will still need, no, the breakwaters. No? Although if it's just a harbor, no, and not a port, no, the marine terminals, no? In particular, no, the docking structures, no, may not be there. No? Well, the function of breakwater, no, is to provide shelter from waves. No? Well, it is the usual case in a harbor. No? Well, there is also another function of the, well, in the case of coastal protection, no? They normally are placed. No? You have a breakwater here, a small one, that's in front of a re-entrant seawall here. No? This is to make sure that the wave breaking occurs at that location and not on the seawall itself, no? Because the seawall does not protect against a wave. No? It protects only against the storm surge, no? Against the storm tide. This one is a breakwater that's used to stabilize an eroding beach. No? So you have these so-called segmented breakwaters. No? They are nearshore breakwaters. They're very close to the shoreline, no? And they make sure that the shoreline stays in place there, no? So that it's not eroded. No? And then you have a harbor, of course, to protect a marina. So it's almost completely enclosing it. No? You have a small entranceway here, no? So that the vessels can move in and out, no, of the marina. And then you have here, no, a harbor that's protecting a coastal jetty. A coastal jetty is not a docking structure. No? By jetty, we use the American parlance, no? That it's a structure that is used to stabilize a river outfall. No? If you have significant littoral material that's carried by the longshore sediment transport, no, they tend to, well, if there is no jetty here, they tend to bypass, no, the outfall. No? If they bypass the outfall, no, sediments tend to settle where the velocities and the waves, no, are calm. No? So they tend to settle there. No? And that is bad, no, for navigation. No? So these jetties are designed to make sure that there is no bypassing of the sand across the river outfall. No? In turn, no, this thing, no, may be subject to extreme storm waves. No? So a breakwater is used to protect that pair of coastal jetties, so that navigation is continuous, no, from inland to the sea. No? So these are some of the types of breakwaters. No? Because we don't have time, no, I will not discuss in detail. No? Just, well, you just look at the pictures. No? Well, we have classification according to the connection to the shore. No? So you have a detached breakwater and an attached breakwater. This one is a well-known, no, port area, no, in harbor area in UK. No? Well, we have, according to crest sighting, you can have an emergent breakwater, no, where the crest is higher than the mean sea level. No? You can also have a submerged breakwater where it's lower, no? Or sometimes called a low-crested, no, breakwater. No? And then you can have according to material, you can have this so-called gravel mound breakwater. No? So normally made up of rocks, no? Angular rocks, no? Or some concrete armor units like tetrapods and dolos and acropods, etc. Then according to material and weight and action, then you can have a vertical breakwater, like this case. No? This is just seabed, no? And then there's a thin, there's no rock foundation. It's just a place on top of the seabed. No? It's a place. This is a reinforced concrete structure with the hollow spaces, no? With the partition walls. No? These are cast offshore. I mean, well, separate from the final position, usually at an onshore site. No? And then this is carried to the site, no, using barges, no? And then they are positioned to the site, no? And after the final position is done, no? The holes in the caisson walls are removed, no? And then it's going to sink. No? And then the upper slab here is cast in situ, no? So that it provides the required monolithic, no? Characteristic, not to the structure. No? This is an example of this so-called caisson breakwater. Yeah, this is a vertical wall. No? So this is an actual photo. I think this one in Spain. No? And this one is what we call a blackwork breakwater, no? Where you have the stacks of reinforced concrete that are so heavy, no? And then they are there is a hole here. No? So after they are cast in place, no? They are stuck in place. No? Then this is a point with the reinforced concrete and some reinforcement, no? So that they act as an integral structure. No? And then you have other breakwater types. No? Well, you have conventional, this one, without any rock foundation here. No? And then if you have a thick rock foundation here, we call it a vertical composite, no? Case of breakwater. No? And then if you have the conventional breakwater, the fronting rock revetment, it's called a horizontally composite, no? Breakwater. No? And then if you have the conventional breakwater, except that the top is now sloping like that, it's called sloping top. No? Well, the sloping nature of the breakwater adds to the so-called external stability, because there is a component of the wave overtopping, the wave force, that is helping stabilize, that helps in stabilizing this caisson, against overturning and sliding. And then some of the modern breakwaters are like this. Now, these are used in more advanced countries that are now harnessing their offshore resources, their offshore wind energy, their tidal in-stream energy, the ocean thermal energy, etc. Well, ocean wave energy can be harnessed, not just by causing the waves to break, but also by putting up some kind of structure shape like this perforated one, so that they can generate power by causing some turbine to rotate, and then by that action, the electricity is produced. Well, these caissons are done like this. They are usually cast in a nearby site onshore, and then they are usually cast like this in modules of about 10 meters by 40 meters, and this is about maybe 40 by 40 by 10 or by 20. This is one is from Pontoa Construction. This is in the port of I think Kanagawa, and then they are brought to the site. So what is done is these are carried by barges at the final position, and then once in the final position, they are sunk by means of pontoons. And once in the final place, these plugs are removed, so that the water can enter. And then finally, once it's in the final position, these open tops are filled with sand. And then they are the top is then cast with reinforced concrete, so that the entire length with these individual modules of the caisson can be considered not to be monolithic. Well, you have other types of breakwater according to the distance from the shore. I will not discuss this. And then, well, you have some of the non large port and harbor areas in the world, like this one in Tenerife, in Spain. This one is in Ogawa port in Japan. And then you have, of course, the in Alderney in UK, you have this so-called black breakwater. You can see the action of the waves splashing on against the seaside of the breakwater. And then this one is in Valencia in Spain. You have this is horizontally composite caisson breakwater. This is used for the navigation. So this sides cannot be reflective. That's why this is a place with a tetrapod revetment. This one is the mammoth structure in Algeciras, Spain. So you have this very long caisson breakwater. This is a vertical composite caisson breakwater. You have here the stockpiling area, the cargo handling area, and you have a secondary breakwater here where the ships can dock and moor. Okay, so this one is in I got involved in this project in Misaki, in port. So you have this a good design of a port, because it exploited this natural feature of the coastline called the Rias coast. This is very unique to Japan. They have this sort of rocky coastline that can be used. Well, they are very resistant to the very erosive action of breaking waves. And they are made part of the design of the main breakwater here, with which is vertically. Sorry, I think this. It's a vertically composite caisson here like this. So you have here the areas for the port. You have the outer breakwater. You have this wharf, and then you have another breakwater, a secondary breakwater. You have an inner bay, where you have a berthing area there, and then a wharf for the ships. Breakwater in Naples, in Italy. This one is in Vieppe, in France. And then Nagashima port, which is designed to also resist, at least mitigate the impact of a tsunami in this area. You have pile breakwaters, then headland breakwaters, And then floating breakwaters. Okay. Well, the most common type of breakwater is rubble mound. No? Generally it's like this. No. So you have essentially an embankment, no, with different sizes of rock. No. Well, the structural part of this rubble mound breakwater is the armor. No? So we design the armor first, no? And then we from the armor design, no, the rest of the cross section follows. And then you have this typical cross section. We normally provide a top protection scar for the seaside, no, armor. No? And then, well, we can see, you know, this rubble mound breakwaters in different places around the world. This one is in the UK. No? I think this one is in Japan. No? And advantage is that it uses natural materials, no? Lower material costs, no? Small construction equipment needed, no? And easy to construct. No? And disadvantage, no, needs a large amount of construction materials, no? If the depth is more than about 8 meters, no? And then continuous maintenance is needed, no? Because the armors got they will be displaced, no? As time progresses, no? So you need to make sure that the number of displaced armors does not exceed, no, the threshold, no, which is about 5%, no, of the initial, no, of the total number. It cannot be used for ship berthing, no, because of the the sloping side and that rough thing. No, if it's going to be used, no, for docking of ship and anchoring of ship, no, the ship anchors and the mooring dolphins, no, need to be placed very far from the breakwater. No? Otherwise, no, the ship's hull can hit them, and it can cause damage of the hull of the ship. We normally design breakwaters based on so-called hydraulic stability criteria, no? An individual armor will not be displaced, no, by wave action. And then there's a formula that we use not to do that. It's called Hanson's formula. No? So that is this equation 18. No? And then we determine the required mass, no, of the armor unit, no, depending on the geometry. No? So you have here the different geometries of the concrete armor. No? Normally it's quarry run rocks. No? If you have a quarry site, no, where you can blast, say, a good, say, basaltic mountain, no? And you can get the required weight, no? Then that's good. No? But nowadays it's hard to do that, no? Because you need to seek the ECC, no, to do the dynamiting and the blasting of the quarry. No? It's not so easy to do that. No? So nowadays, what we call concrete armor units, no, which are engineered geometries, no, that are used to provide the unit for the armor layer of the rubble mound breakwater. These are some of the geometries. No? The most common is this one, tetrapod, no? The core lock. No? This is a Dutch copyright. No? Yeah, but it's now in the public domain. Anyone can manufacture this. No? Core lock is an American invention, no? From the U.S. Army Corps of Engineers. Acropole is a French invention, and then we have other. Dolos, no, is a Dutch, no, material. No? Well, you have other geometries. No? Nowadays, geometries like this, no, like the cubipod, no, and the antifer, no, and then the tetrapod. Of course, tetrapod is E, no, and then this one, no, is X block. No? So this one is in, I think, in this one is in the where's this Maldives, no? So you can see the size of that X block, no, relative to that engine. Okay, so there is a sample, simple design exercise, no, for the armor layer of the rubble mound breakwater. But if you're interested in this, no, please refer not to this slide. Okay, quay walls, no, or quay walls, no. These quay walls, no, are very important infrastructure, no, of ports, no, especially those ports that are catering not to, say, passenger ships, no, because passenger ships have more, shall we say, stringent requirements, no, for the thresholds of ship motion. No? So you can see these quay walls, no, for example, here, no, in UK, no. So you can see the structure. No? So you can see that it's a lattice type, no, it's not a solid wall. No? And the reason is that, no, these quay walls, no, prevent, no, the reflection, no, the penetrating waves, no, in the harbor. No? If these waves are allowed to, return to the sea, no, they will cause an undesirable phenomenon called seaching. No? And we don't want seaching to occur. No? Seaching means that if you are inside the harbor, no, if the design is bad, no, then the wave height inside the harbor is bigger, no, than outside, no, which is an undesirable condition. So to prevent that, no, quay walls are designed, no, for mostly, passenger ships, no, that require, no, a smaller, no, threshold of ship motion, no, because of passengers. No? Well, you have these quay walls in some parts of the world. No? Well, in Netherlands, no? This one is in Rotterdam, no? And the old quay wall is being rehabilitated with this design. And in Greece, no, they have this design of perforated, no, caissons, no, like this, no, with the hollow blocks, no, like that. So these are quay walls, no, that are quite unique, no, to Greece. No? Our own Port of Manila, no? It's something like this, no? But it is not. It's not in the Port of Manila, no? But our quay walls are of this type. No? Well, the design of the quay wall, no? If you look at the plan form of a quay wall, it's like this. No? You have lattice there, no? With intersecting blocks, no? Of what we call these blocks of concrete, no? And what they do is they decrease the reflection. No? So, for example, this is the reflection coefficient. No? From a high value of 0.6, no? They are able to reduce it to just 0.1, no? Which is good enough. Okay, so I think this is the last slide, no, for this topic. Meron pa bang time? I think it's only up to 4 o'clock. No? So I see that already. Tama ba, Angelo?
Yes, sir. Go ahead. Apo.
Sige. So this is my last slide. No? Thank you for your attention. Sorry, I couldn't finish everything. No? The next part would have been the mooring structure, no? And design of the fixed structures inside the port, no? Like the pier, no? And subsea pipelines, no? To carry for example, the fluid, no, or the gas, no, from the ship to the onshore facility. No? I couldn't reach that. No, sorry. If you are interested, no, in these topics, no, I'll give you the material, no, for these topics. Thank you, no, for your attention.
All right. Thank you, Engineer Cruz, for that thorough and comprehensive discussion on coastal and port engineering. So now we'll open the virtual floor for questions. So for the participants who want to ask questions directly, please press the raise hand icon. And we will also be reading the questions posted in the chat box. So do we have any questions po from our participants? So if none, thank you everyone. So that concludes our 6th plenary session. We once again thank Engineer Eric Cruz and his technical assistant, Miss Georgia Assistine, for all your time and effort in devising this coastal and port engineering course. And most importantly, we thank all the agencies and LGUs for attending. Ayan. Thank you very much, everyone. Have a great weekend.
Thank you, ma'am.
Thank you, everyone.
Thank you.
Thank you, ma'am, sir. Thank you.
Thank you, ma'am. Thank you, sir.